We propose a novel 360-degree scene representation for converting real scenes into stereoscopic 3D virtual reality content with head motion parallax. Our image-based scene representation enables efficient synthesis of novel views with 6 degrees of freedom. As you can see in the video, the rotation and translation of HMD will cause different foreground-background position changes. This sort of changes cannot be achieved in nowadays stereo panorama images. This is the agenda of today's presentation. We will first introduce the problem we are working on and compare some of current related work. Currently, the most convenient way to visualize a real 360-degree scene within a head-mounted display is to use a panorama or stereo panorama. However, no matter it is panorama or stereo panorama, it is made by static images, which means there will be no head motion parallax in the view. As we can see in this video in the right, there will be no occlusion relationship changes with the viewpoint. A virtual 3D scene can be very efficiently rendered if it is available in the form of textured geometry. Using depth sensors, larger scenes can also be reconstructed. However, current 3D reconstruction techniques cannot handle large outdoor scenes yet because we lack ability of reconstructing distant objects or achieving multi-view coverage of all objects. On the other hand, scenes can be represented purely with images and without any geometric information such as the light field or lumograph, some image-based rendering methods. Using the light field or lumograph can represent scene purely with images and without any geometric information. This kind of methods require extremely densely sampled images of a scene, but it is impractical for a 360-degree scene. Thus, we need a method to handle outdoor scenes with distant objects and less densely sampled images but still provide head motion parallax. Our 360-degree scene representation consists of 3 types of information: keyframes for color information of the scene, disparity motion fields for implicit 3D information at each keyframe, pairwise motion fields for efficient and smooth viewpoint transitions in novel view synthesis. We capture keyframes at uniform angular increments of 5 degrees in both latitude and longitude on a sphere with a diameter of 1.25 meters. Besides the keyframes, we also capture another kind of frames, called relative frames. We use relative frames to compute the disparity motion fields. Relative frames are captured on a circle centered at the keyframe position, with a fixed radius of 25 mm in our experiments. To capture the keyframes and the corresponding relative frames for a real scene, we developed the captured device. It is a robotic arm with 3 degrees of freedom to control the position and orientation of a camera. We capture a range of 360 degrees horizontally and 40 degrees vertically in steps of 5 degrees. Our device captures the corresponding 576 keyframes and 3456 relative frames in less than 2 hours. This time can be reduced by using faster stepper motors. Inspired by the motion compensation techniques used in video compression, we use motion fields to synthesize new views. We start by computing optical flow between the keyframe and all its relative frames. We aggregate the motion vectors of individual pixels into non-overlapping image patches of size 8 × 8 pixels by averaging them. To merge the individual motion vectors of the relative frames into a single disparity motion field, we propose a curve-based motion representation. Based on this motion representation, we can obtain the target motion field for the novel viewpoint by estimating the motion vectors for all patches accordingly. The left figure is a sampling circle with 6 relative frames, and the target viewpoint, the right one, is the motion vectors of the patch in the 6 relative frames, and in the target frame we fit an ellipse by least squares fitting. to the endpoints of all 6 motion vectors to encode the motion magnitude. Now we only lack the pairwise motion fields for efficient and smooth viewpoint transitions in novel view synthesis between keyframes. We compute the pairwise motion fields between every pair of neighboring keyframes using optical flow. These pairwise motion fields are also stored in our scene representation and make it complete. For a target viewpoint on the sampling sphere, we first find its k-nearest keyframes, ordered by distance. We use this disparity-derived motion field to synthesize the target view. To synthesize a final target image IT without ghosting artifacts, we align the target images of all keyframes using flow-based blending. We estimate the blending motion field using optical flow from target image I1T to target image IKT. Another obstacle that prevents achieving real-time performance is the calculation of the blending flow fields. We propose to use the pre-computed disparity and pairwise motion fields to infer this blending flow field instead of calculating optical flow between the target images online. Let's see some experiments of our work. In the stereo panorama, the rendered images are keeping the same positional relationship when HMD is rotating. However, users can see behind the statue's leg within our approach. Suppose one user is really looking at the scene, the occlusion between the flower pot and the vase should change with their head rotation, but this cannot be observed in the stereo panorama, where the flower pot is permanently hidden behind the vase. In our results, one can clearly see the change of position between the large vase and the small flower pot behind it. To further evaluate our method, we compare 3 different solutions for synthesizing novel views. Nearest keyframe renders a novel view using only the nearest keyframe. Flow-based rendering renders a novel view using our full rendering method. Alpha blending renders a novel view using the nearest k equals 2 keyframes. In NKF results, there is abrupt changes when HMD is rotating while switching from one keyframe to another. In A/B results, the abrupt changes disappear, but the rendered view contains obvious blurriness. Our FBB rendering method trade-off these two methods with smooth transition effect. Let's have some discussion and talk about the future work now. Pre-computation of our work takes almost 24 hours on a quad-core PC. Thus, we suppose using a real-time optical flow method may reduce our pre-computation time. With storage problem, all the data is required to achieve head motion parallax. We believe some compression schemes used for light fields could likely be adapted to reduce storage requirements. The last but not the least, if the optical flow we pre-compute contains errors, the final results will likely contain artifacts. We can try to enforce some geometric consistency checks to our representation in the future work. Some more discussion on capture device. Light Fields team at Google as part of Daydream's immersive media strategy is releasing these images. It is similar to our capture device, but with more cameras. To conclude this speech, we proposed a complete system for capturing and representing a real scene and rendering it in a VR HMD in real time. Our work contains a novel image-based representation for 360 degrees real scenes and a robust curve-based fitting method for estimating disparity motion fields. Experiments show smooth viewpoint transitions with minimal visual artifacts using our FBB rendering method.